Hello everyone. In this video we're going to discuss about chapter 2, where we have force and motion in one dimension. Right, so for the first week of this chapter we're going to discuss 2.1 and 2.2. Alright, so I combine these two together so that we can see the overall relationship between force and motion. Right, so here in this handout, as you can check, I put first the definition of force. So force is defined as an influence that can cause a change in motion of a body or cause a stationary body to move. Very simple here. Something that can cause change in motion of an object we call as force. That's it, that is a force. Anything that can move object or stop the object we call as force. Alright, so when we discuss about force, there are three Newton's law, very important here. So the first Newton's law talk about a particle will remain at rest or continue to move with a constant velocity in a straight line unless acted upon by external force. Very simple here to understand this law. So if you have an object, for example, on the horizontal floor, if there is no force acted on it, so the object will remain at rest. And if the object moves with a constant velocity, it will continue forever and forever until there's a force stop it. And for the second Newton's law, this is very popular law from Newton's. We have summation of force equals to mass multiplied by acceleration, right? And next one is third Newton's law. So here it's mentioned every action has an equal opposite reaction. So example for this, if let's say you think about you push a wall with your hand, somehow you put force to the wall, and the wall, as you push the wall somehow react with equal and opposite force to your hand. Alright, or you can think about when object on the horizontal floor, the object got weight vertically downward, and opposite of that weight force we have normal reaction force from the floor acting up. Alright, so that's three Newton's law we have in this syllabus, but no worries everyone, because in our syllabus the question will not ask to state the law of Newton's. Alright, okay, so as you can see in this note also I mentioned about unit force. Right, so for the force, the unit we use is Newton, and we need to know that 1 Newton is equals to 1 kilogram meter per second square. Alright, we can see the relationship between 1 Newton equal to 1 kilogram meter per second square in the second Newton's law. Right, so as we know that mass is measured in kilogram and acceleration is measured in meter per second square. So 1 Newton equals to 1 kilogram meter per second square. Alright, and here also in the last point we have here object with net zero force acting on them are said to be in equilibrium and have no acceleration. This is the case of equilibrium. So if object or the system in equilibrium, then summation of force in any direction on the object is equal to 0. Alright, and there are a few type of force in our syllabus. This is just for our reference, not all, but this basically list of force that we can have in mechanic. Usually we have it. So we have weight force, tension or thrust, resistance force, braking or driving force, normal contact force or normal reaction force, and lastly we have friction force. Okay, all of it we're gonna see in this mechanic syllabus. Alright, next part is about force diagram. This is basically require in the syllabus. You need to know how to draw a force diagram, and there's also question asked to draw force diagram. Okay, so make sure you know how to draw force diagram. Okay, let's see this. We have a simple example where let's say for example we have an object, and on the object over here we draw as just a small box or small square, and if there is a force act on object horizontally, so how we draw, basically we have an object like this and it is on horizontal floor and there is force act on it horizontally, so we take from the middle of the box, drag, and we put arrow to the right and we write the letter F to represent force that act on object horizontally. Right, horizontally can be to the right, can be to the left, but basically for this case I draw force acting horizontally to the right. Okay, and the other example where, for example, let's say we have same case where we have an object on the horizontal floor and there are few forces acting on it. For example, let's say we have force 1, okay, act horizontally to the right, and let's say there is another force act horizontally to the left. Let's denote this as F2, and maybe we can have also a force that act vertically. It usually we call as this one as a normal reaction force, and usually we denote as R for the normal reaction force. Okay, so as you can see from my force drawing, I use a bit long arrow diagram. Okay, before this, as we have in the chapter 1, we have a small arrow diagram for the velocity and small double arrow diagram for the acceleration. So make sure for the force we draw a bit longer compared to velocity and acceleration to represent force. Okay, that's basically how we draw force diagram. And basically we're going to see another force diagram example when we discuss about next and the following example. Okay, right, so now we move to the next page. So for the next page we have the example 1, very basic example where we have 3 questions there. So as you can see, let's for example 1a, we have case of to find horizontal force required to make a car of mass 500 kg accelerate at 2 meter per second on horizontal road. So for me, I will suggest that student to sketch force diagram. So for example, for this case we have horizontal road and there is a car on the road with a mass of 500 gram and its acceleration is 2 meter per second. Alright, and we need to find force required to move the car at acceleration of 2 meter per second square. So for this case we're going to use a second Newton's law. We have force is equals to ma. So what force act on object? Only F. Alright, so for that case F is equals to force F is equals to mass of the car, it is 500, multiplied by acceleration 2. Right, so required force to move this car at a constant acceleration of 2 meters per second is 1000 Newton. Alright, that's it. And how about for B? So for B, we have a wooden block of mass 300 gram is being pushed along horizontal surface by a horizontal force of 1.2 Newton. Find its acceleration. So they give us a mass, they give us the force. So again, actually without the force diagram we still can solve this. Alright, but however, since we want to practice draw force diagram, we just draw the force diagram to illustrate the problem. Okay, so for this case we have an object, a wooden block on the horizontal surface, and the mass given here is 300 gram. Okay, be careful, the mass given here in gram, so make sure we convert gram into kilogram. So we're going to get 0.3 kilogram. Okay, so and force applied to the object is 1.2 Newton. Right, we are required to find its acceleration. So again we're going to use force equals to ma. So force applied to object is 1.2 and then mass given here is 0.3 in kilogram multiplied by acceleration. So acceleration is equals to 1.2 divided by 0.3. So you're gonna get it is equals to 4 meter per second square. That's it. And I leave question C for you to try. Okay, and you can check the answer for this question C is 300 kilogram. Okay, please make sure you check this question. Okay, for example 2, we have a man push a boy in a trolley with a total mass of 60 kilogram along horizontal line from rest with a constant force of 42 Newton for 10 seconds. Find the distance traveled in this time. So as you can read this question, they give us that initially it pushed from rest, so means that our initial velocity is 0, and with a constant force of 42 Newton for 10 seconds we want to find the distance travel. So how to find the distance travel here? So for this case, as we want to find the distance, we need to use Suvat equation. We need to apply Suvat equation that we have learned in chapter 1. But before that, in applying the Suvat equation, we need to list all the values related to the Suvat equation we need to use after this. So here, let's list out what we have. So initially, velocity is 0. Okay, and then yes, we have given the t, so t is 10 seconds. And how about final velocity? We don't have it. We don't have this. And how about acceleration? We also don't have this. But relate to the second Newton's law that we have in this chapter, we can find the acceleration by using second Newton's law, right? So for this case, we have to find acceleration first. But without the final velocity, we still can find the distance, right? By using s equals to ut plus with half of at square. So here, in applying this equation, we just need to have initial velocity. Yes, we have time also, and we need to find the acceleration, right? So for this case, let's find the acceleration first. So we can find the acceleration by apply the second Newton's law. So we have F equals to ma. So what force involved here? So as we illustrate with the diagram, we can have boy with a box, and then there is a force, a push force over here. Let's denote as F from man, and we have mass of ball and trolley. It is 60 kilograms. So again, we apply second Newton's law here. So force given here is 40 Newton, and mass we have here is 60 and multiplied by A. So A is equal to 42 divided by 60 kilogram. So we will have A is equal to, A here is equal to 0.7 meter per second. So back to our Suvat equation here, s equals to ut plus half of at square. We plug in all the value that we have here. So s is equals to 0 times with 10 second plus with half of 0.7 multiplied by t square. So it is 10 square. So we calculate this, we're gonna get distance travel for the 10 second is 35 meter. Right, that's it. This is answer for example 2. Alright, next example, example 3, we have a little bit different problem. Let's say this: a car traveling along a straight horizontal road produces a driving force of 1.27 kilonewton whilst experiencing a resistance force of 190 newton. The car takes 15 seconds to accelerate uniformly from 4 meter per second to 22 meter per second. Find the mass of the car. So here I would like to suggest we draw force diagram on the car, so that we will see what forces act on the car here, and also we need to know the direction of forces add to the car. Right, so here we have horizontal road, okay, and then we have car represented by box there, and then we have driving force of 1.27 kilo, so it is equivalent to 127 Newton. I assume the car moved to the right here with driving force of 1270 Newton, and then at the same time the car experiencing a resistant force of 190. So any kind of resistant force, it always opposes the motion. So for this case, driving force to the right, and of course the car move with a constant acceleration to the right, and for the resistant force, we draw its opposite direction of motion. It move to the left. The direction of resistance over here is to the left, right? So it is 190 Newton. So we have two force over here, which is driving force to the right, same direction of motion, and resistance of 190 to opposite direction of motion. Alright, so it moves with constant acceleration, of course, and it take 15 seconds. It take 15 seconds to move from 4 to 22 meter per second. Alright, so we want to find the mass of the car here. Right, so to solve this, of course, we need to relate second Newton's law and also solve the equation. Alright, so here, think about it. We want to find the mass. Alright, so mass variable, we can have it in the second Newton's law, because in second Newton's law we have F equals to mass multiplied by acceleration. But before that, we don't have the acceleration, right? We don't have the acceleration, so we need to find acceleration first, right? So to find the acceleration, we need to apply Survey equation. So let's list out what we have here. So to apply Survey equation, yes, we have initial velocity, it is 4, and final velocity, it is 22, and we also given the time. It take 15 seconds from 4 to 22 meter per second. So the time taken here is 15. Right, so what the best formula to use here? It is V equals to U plus AT. Right, so V is 22, initial velocity is 4, plus with acceleration, the thing that we need to find, multiply by 15. So calculate the value of acceleration here. We will get it is equals to 1.2 meter per second square. Right, so come back to our second Newton's law, F equals to ma. Alright, so what force involved in the system? So we have driving force and resistance. Alright, so for this case, I will put the small arrow to the right, as for our assumption to the right is positive direction. So for this case, any force same with this arrow diagram, we're going to put as positive. Any force that opposite direction of this arrow become negative. So we're going to write like this: 1270 minus with 190 from the resistance is equals to mass multiplied by 1.2, which is the value of acceleration that we calculate just now. Right, so this is basically sum of force at an object. Alright, so in general we can write summation of force is equals to ma. So any force in direction of motion become positive, and any force in opposite direction of motion become negative. Like we have here, it is negative 190 because it is opposite direction of motion. Alright, so to calculate this, just simplify the equation. We're gonna get m is equals to 900 kilogram. That's it. Alright, okay. Next example 4 here. Alright, so let's see the question. A car of mass 600 kilogram has a driving force of 500 Newton and air resistance of 200 Newton. Okay, so let's illustrate the problem first. Okay, from the main question, we have a car of 600 kilogram has driving force. So driving force in direction of motion, of course, it is 500 Newton, right? And then opposite of direction motion, we have air resistance of 200 Newton. So air resistance will be opposite direction motion to the left here, so 200. So we draw a small double arrow diagram for the acceleration to the right. Okay, now for the question A, find how long it takes to accelerate from 10 meter per second to 22 meter per second. Actually, this is typo, is actually 22 meter per second, not meter per second square. So we want to find the time taken to accelerate from initial velocity of 10 meter per second to 22 meter per second. Alright, so let's illustrate again on the diagram here. So initially we have initial velocity of 10, and we want to find how long it takes to come to a velocity of 22 meter per second. So how to solve this? Again, this is the case of two concepts, alright, where we have to find the acceleration first, and after that we need to apply Support equation. So let's say this. So step by step, first thing first, in order to apply Support equation, we need to find the value of acceleration first. So here look what force involved in the system. So force from the driving force 500, and then we have resistance of 200. Okay, from there we can find the sum of force, and then equate with the mass, and then multiply with acceleration. So how we write it? So basically we have 500 positive force minus with 200, and then it is equals to mass of 600 multiplied by acceleration. Right, so we can get the acceleration over here is equals to 0.5 meter per second square. Alright, next we want to find the time taken from 10 meter per second square to reach 22 meter per second. So how long you're going to take, alright, to accelerate from this point to that point. Okay, now which is the best formula to apply here? The best formula is of course V equals to U plus AT. So final velocity is 22, initial velocity is 10, and our acceleration for the system is 0.5, and multiply by T. So time taken is equals to, what do you get here? You should get 24 seconds. So you need to think about, in order to accelerate from 10 to 22 meter per second, it takes 24 seconds. Okay, alright, so that's for question A. How about for question B? For question B, we have a new information here. So the car stopped providing a driving force, and the brake force are applied. Okay, it's decelerate from 22 meter per second to rest in 220 meter distance. Right, so initial velocity now is 22. Right, so this is our initial velocity. Okay, this is our initial velocity, and then come to rest means that final velocity is 0, and it take 220 meter distance to coming to rest. Okay, so the question asks to find the force of brake over here. So let's illustrate with new diagram. Okay, we're going to use this diagram, but since it said that the driving force are removed, so means that now we remove of 500 Newton force. 500 Newton force is removed there, and then the brake force is applied. So remember I told you just now, any kind of resistance, brake force, and synonym with that, it always oppose the motion. Yes, the motion is still go to the right, but braking force is something force that prevent the motion. So we draw brake force to the left here. So let's denote as F sub B. Okay, F sub B represent braking force. So in order to solve for the braking force, we need to find first acceleration with Support equation. Okay, so for this case, the solution for B will be applying Support equation, and after that apply second into law. So what is the best formula to find the acceleration? We are given now, okay, but before this we need to change this. So find initial velocity given for the question B is 22, and we want to find braking force with this initial velocity where final velocity becomes to 0, and then given also distance coming to stop is take 220 meter. Okay, so now our information do not have time. We have final velocity, we have initial velocity, when also, and y also we have also distance. Okay, so for this case, the best formula to apply here is v square equals to u square plus 2as. Okay, this support equation not require time to find respective variable, right? So for this case, this is the best formula to apply. So v square is 0, so just plug in the value, and initial velocity is 22 square root plus with 2 times with a, the thing that we need to find here, multiplied by distance travel from 22 to 0 meter per second. Alright, so we're going to get the acceleration here is equals to negative 1.1 meter per second square. Right, when we get the acceleration, we need to check carefully. Yes, our value of acceleration is negative, and it is logic enough because initially we have 22 meter per second, and it slowed down, and then coming to initial velocity, coming to a velocity of 0 meter per second. Right, so obviously we're going to have negative acceleration, and our value that we have calculated just now is correct. Right, so when we get this acceleration, then we're going to apply the second Newton's law. Right, so look back in our force diagram. What force involved here? We have braking force acting opposite direction of motion, and we have air resistance also acting opposite direction of motion. So both of these force must be negative in our equation of second Newton's law. So we're going to get negative Fb minus with 200 Newton force equals to mass of the car, which is 600, multiply acceleration that we have calculated just now. It is negative 1.1. Right, and then after that, calculate the value of braking force. Over here, we're going to get it is equals to 400 Newton. Please make sure you check this example. Right, that's it for example 4. And for the next page, we have example 5. I leave this example 5 for you to try. Okay, please try it. And the answer for this example 5 is equals to, we want to find the speed, right? So the answer for this one is speed is 160 meter per second. Please check out this example 5. And of course, over here at the bottom of the page, we have try question. So make sure you try this question also, and you can check the answer for first question try is 4000 Newton force, and for the second try question is 1 to 5 Newton. Right, please check these two example try by yourself after you watch this video. Alright, so next subtopic is 2.3. We have weight and motion due to gravity. Right, so in previous chapter 1, we have discussed about vertical motion, motion that under the gravity, right? But in that chapter, we do not have force at an object, because object just move freely under the gravitational acceleration. But this time, when we talk about force and motion due to gravity, we need to consider the force at an object, especially the weight, plus with any other force at an object when the object move vertically. It's either up or down. We need to consider all of it. Alright, so now let's see definition of weight. So here we have simple definition of weight. Weight of an object is a force caused by gravitational acceleration experienced by the object. Very simple here. So we can get the force of weight by taking mass multiplied by gravity. So again, mass in kilogram, gravity in meter per second square. So you're gonna get unit for the weight is also 1 Newton, and it is equivalent to 1 kilogram meter per second, as we have in the normal force that we have before this. Alright, so that's the weight. And here I want to stress that weight is not equals to the mass. Again, weight is equals to mass multiplied by gravity. Alright, so weight is force, mass is not force. Okay, mass basically is composition of a body, and weight is a force, and it has direction, and the direction is always at vertically downward here. So as we draw the weight force diagram, so we have here is, for example, let's say we have an object on the flat surface, and how we draw weight force, it take from the middle of or the center of the object, and it's acting vertically downward. That's how we draw weight force, and it is always vertically downward whatever the surface. So it is equals to mass multiplied by gravity. Okay, this is one of example. If let's say we have a slope surface, for example, an object on it, so weight acting here is always vertically downward. It is equals to mass multiplied by gravity. Again, weight is always acting vertically downward. That's important there. Alright, and let's see for example here. We have example 1. A ball of mass 120 gram is dropped from the top of tower of height 25 meter. The ball experiences an air resistance of 0.03 Newton as it falls. Find how much longer it takes for the ball to hit the ground than if air resistance were ignored. Okay, so here we want to compare between with air resistance and without air resistance. So before this, remember, I just want to remind all of you again, in the chapter 1 we have the case of vertical motion or motion due gravity without external force, but this time we have external force, which is here is referring to the air resistance force. Okay, so the acceleration of the object is no more equals to gravity. Okay, but if the case of air resistance were ignored, that case is case of free fall motion, and the acceleration of the object is equals to gravitational acceleration. So let's see first for the first case with air resistance. So with air resistance, so with air resistance, acceleration is not equals to gravity anymore. Okay, so for this case we need to find a new acceleration, right? So for this case, object is moving from top of tower moving down. Alright, so for this case, if you want to illustrate, we have an object, and then force acting on it, of course we have weight vertically downward. It is equals to 0.12 multiplied by 10, the value of gravity, and then it is acting downward vertically, and then as it moving downward with a constant acceleration a, there is a resistance acting up. Okay, remember, any kind of resistance force, it always opposes the motion. Since our motion is going downward, air resistance is acting upward. The value here is given 0.03 Newton. Okay, so these are the force acting on the object. We have weight force vertically downward and air resistance acting upward, and the motion of course going downward. Right, so for this case we need to find our acceleration first, the acceleration of the motion. So we need to see what force involved here. So we have weight force and air resistance. So weight force is positive because same direction of motion, and resistance is negative because it is opposite direction of motion. So how we write the equation? We're going to write as 0.12 multiplied by 10 minus with air resistance 0.03 equals to mass of the object. It is 0.12 in kilogram multiplied by acceleration. So solve for the acceleration, we're going to get acceleration is equals to 9.75 meter per second square. Right, as you can see, the acceleration over here, as air resistance acting opposite direction motion, the acceleration is not equals to 10 anymore. We will have here it is equals to it is 9.75 meter per second. Alright, so for this case, in order to find the time taken to reach the ground, we're going to use Savart equation. Alright, since the displacement given here is 25, so we're going to use 25 equals to ut half of f plus half of at squared. U is 0 times with t, the thing that we need to find, plus with half of acceleration 9.75 multiplied by t square. And you're going to solve for the velocity here from this quadratic equation. You're going to t is equals to 2.26 seconds, and the other solution for the t is negative 2.26 seconds. So we're going to consider positive value of t here. So the value of t for the time taken from the top of the building to the ground, we're going to take 2.26 seconds. This is case of with air resistance. How about without air resistance? Without air resistance, then we consider acceleration is equals to gravity. It is equals to 10 meter per second, and we're going to find how long it takes from the top of the building to the ground. So again, this is basically reverse what we have learned in chapter 1. So we just apply Stewart equation here. So displacement here is 25 equals to 0 times with t plus with half of 10 t square. So solve for the value of t and consider the positive value of t. We're going to get 2.224 seconds, basically 24 seconds. Alright, so because we want to find how much longer it takes for the ball to hit the ground, so we're going to take the difference here. So the difference of t here is modulus of 2.26 minus with 2.24 seconds. So we're going to get 0.03 seconds. So with air resistance, it takes 0.03 seconds longer compared to the case of without air resistance. That's it. That is for example 1. Alright, so next example is example 2. Okay, so for example 2, we have two questions, A and B. But here in this video, we're going to discuss for question B only. So for question A, please make sure try yourself. Alright, and this is actually you can refer from the textbook. Right, so for now, let's start discuss question B, example 2, question B. So here, yes, from the question A, we have a ball of mass 0.2 kilogram is thrown vertically upward out of window 4 meter above the ground. The ball is released with a speed of 4 meter per second. And for question A, it is assumed no air resistance and find how long it takes to hit the ground. Okay, so hopefully you can settle this question A. Now we have problem for question B, where if instead there is a constant air resistance of 0.1 Newton against direction of motion, find how long the ball takes to hit the ground. So we want to find time taken from its starting point to the ground with case of air resistance. Okay, this question looks similar to what we have in the example 1, but in example 1 we have one direction of motion only, from the top of building thrown vertically downward to the ground. But this example 2, we have two direction motion, it going up first, reach maximum, and then after that going to the ground. So if you want to illustrate the problem somehow looks like this. So start from 4 meter level from the ground, and then with initial velocity of 8 meter per second. Right, so the ball somehow start from this point, go up, reach maximum point, and then after that go down to the ground, and we're going to find how long it take. Okay, so for this case, the case of air resistance, remember for case without air resistance, I hope you can do yourself. Alright, because we have discussed this kind of problem many times in the chapter 1. Alright, so for this case, for solving question B, my suggestion is divide the motion in two stages of the motion. So first stage of motion is stage of going up, and then after that stage going down. Okay, why we need to do that? Because remember, we need to consider force act on object. So when object going up, force act on object will be weight force vertically downward. It is 0.2 multiplied by 10. Alright, mass multiplied by gravity for the weight, and then air resistance acting opposite direction of motion. So since the object move up direction, so air resistance acting downward with a value of 0.1 Newton. Okay, and for the case of going down, what force involved there? Alright, let's see this. So yes, weight is always vertically downward. It is equal to 0.2 multiplied by 10, and then since the object is moving downward, air resistance will be acting upward with a value of 0.1 Newton. So as you can see here, we need to divide going up and going down individually and solve individually, of course. Okay, so for this case, let's solve time taken from its initial point to the maximum point first. Alright, so for this case, we need to find acceleration. Okay, so acceleration for going up will be F equals to ma. We need to apply F equal to ma. So what force involved here? Since both of the force over here is opposite direction of motion, so how we write the equation? We write equation as -2 is from the weight force minus with 0.1 from air resistance. Why both of these negative? Remember, because these two force are in different direction of motion or opposite direction of motion. Okay, and then we equate with mass multiplied by acceleration. The mass here is 0.2 multiplied by a, the acceleration. So solve for the value of a, we're going to get it is equal to negative 10.5 meter per second square. Okay, so and after that, we know that as the object start from 4 meter level going up to maximum, and at maximum point we know that velocity is 0. So for that case, we can use subvert equation v equals to u plus at. So v at the top or at the maximum height is 0, so 0 equals to initial velocity given here is 8. Okay, from part A you can see that 8 plus with a is negative 10.5 multiplied by t. So time taken for the object to going up to maximum height is take 0.762 seconds. Okay, that is time taken from its original position 4 meter above the ground to the maximum height. Okay, alright, so next part is we want to find time taken from the top height or from the maximum height to the ground. Okay, so before that we need to find first what's the distance from a starting point to maximum height. Alright, so that we can get the full distance or full displacement from the ground to the maximum height for net solution. Alright, so for that case, we need to find, we need to find S1 first. Okay, it's present S1 here is represent from its original position to maximum height. So for that case, we can find by using v square equal to u square plus 2as. So v at the top or at maximum height is 0, so 0 square equals to u square. So u square is 8 square plus with 2 times with acceleration going up. Acceleration of going up just now is negative 10.5 meter per second square, and then s1 multiplied by s1 there. So we're gonna get s1 is equals to 3.048 meter. So yes, we have already, it is 3.048 meter. 48 meter. So distance from the top or maximum height to the bottom or to the ground will be 7.048 meter. Right, so I'm going to use this value of s in solving time taken from the maximum height to the ground after this. Right, now we focus on time taken from the maximum height to the ground. Okay, so first thing first, we need to look what force involved here. So what force involved here is, yes, vertically downward, we have weight, and then since the object from the top going downward, we have air resistance acting up. Okay, so for this case, we can apply second Newton's law again to find acceleration going downward. What the value of acceleration going downward here? So F equal to ma. So what force involved here? Since downward is direction motion, so we assume downward as positive. So for this case, we're gonna get 2 minus with air resistance. Why minus? Because air resistance is acting up and it is opposite direction of motion. So we're gonna get negative 0.1 equals to the mass of the object. It is 0.2 multiply acceleration going downward. So acceleration here we will have is equals to 9.5 meter per second square. Okay, so it is positive here when it going downward. So from the top to the ground, we have already S equals to 7.048 meter. So with this value of A and the value of S we have there, with initial velocity at the maximum height, we want to find time taken from the maximum height to the ground. So for that case, we're going to use S equals to UT plus half of AT square. Okay, so S is of course 7.048 equals to initial velocity at the maximum height, it is 0, time with T, the thing that we need to find here, plus with half of acceleration going downward, it is 9.5 meter per second square multiplied by T square. So solve for the value of T, you're gonna get positive and negative value, and for this case we're gonna consider positive value of T. So it is 1.22 second in 3 significant figure. Okay, so time taken from the maximum height to the ground take 1.22 seconds. So the total time taken from its starting point of 4 meter from the ground to the maximum height and maximum height to the ground, it is what here? So we're gonna take total time here 0.762 second plus with 1.22 second. So the total time taken here is 1.98 second. That's it. With this value, I hope you can compare the value of T that for the case of no air resistance. Okay, make sure you check this example. Alright, for example 3, I hope you can try yourself. Same goes to example 4. I hope you can also try yourself for this example. So for this example 3, the answer is 1430, or it is equivalent to 76.7 meter per second. Please check yourself for this example. Same goes to example 4. It's actually just a simple example. So the answer for this question asks to find the height at which it explodes. The answer is S equals to 150 meter. Right, so hopefully you can check yourself this example 4 and example 3. And besides that, as you move to the next page, we have try question. So for this try question is actually interesting to try, so hopefully you can try also. And the answer for question 1, you will have 7.56 meter per second. And for question 2 try is question A, you're gonna get 13.5 Newton. And for question 2B, because the question asks you to show, right, so you sketch this one. Chat with your friend for the question 2B. Alright. Okay, subtopic 2.4, normal contact force and motion in vertical line. Okay, so for this case, we have normal contact force. So the name itself, normal contact force. Contact means that normal contact force only exists when there is contact between two surfaces. Okay, for example, let's say we have an object on the flat surface. So for this case, we have surface of object contact with the surface of the floor. Basically, at the bottom of the object we have surface contact with the floor surface, so means that there will be a reaction force. Okay, the other name is reaction force here. So as you can see here, if an object in contact with a surface, the object will experience a reaction force, or known as normal reaction force. And the direction of normal reaction force is always perpendicular to the surface. Alright, as I put in this note, reaction force is always at perpendicular to surface. Okay, so for this case, how we draw normal reaction force? Alright, so remember in the previous subtopic, we have weight. So for this case, weight is vertically downward. It is equals to mass multiplied by gravity. And for the case of normal reaction force or normal contact force, it acting perpendicular to the surface, right? To the surface. So for this case, how we draw normal reaction force? It is actually from the surface, floor surface, acting to the object vertically up. And usually we denote as a capital R for the normal contact force or normal reaction force. Okay, and it is always acting perpendicularly from the surface. That's it. And let's say if the surface is slope surface like this, for example, and there is object on that surface, so how we draw normal reaction force for this case? Again, remember, reaction force is always at perpendicular to the surface. For this case, from the surface, or from the surface, from the slope surface, it is acting perpendicularly from the surface, so it's acting up to the object. So this is normal reaction force, and the direction is perpendicular to the surface, like that. Alright, so if let's say we have another case, for example, let's say we have a vertical surface wall. For example, we have a vertical wall and there is an object attached to it, so means that there is a contact between surface of the object with the surface of the wall. So normal reaction force we draw for this case will be to the left. And why to the left? Because normal reaction force is always acting perpendicular to the surface. Okay, so for this chapter we're going to see for the case of vertical line only, for the case of the first force diagram, and for the other case we have here, we're going to see in the following chapter. Alright, so that's it. So for this case of normal reaction force, if let's say we have an object on the flat surface and there is no external force at an object, so we have here just weight force vertically downward and normal reaction force vertically upward. So easy for us to calculate the normal reaction force. So normal reaction force minus with the weight is equal to 0. So normal reaction force equals to weight for this case. However, for the case of slope surface, normal reaction force is not equals to the weight. Okay, so in general I can say that normal reaction force is not necessarily equal to weight. We need to resolve and consider all forces at an object and what force acting parallel to the normal reaction force, and we need to consider all of it to calculate the normal reaction force. Okay, alright, so let's see example 1 so that we can have better understanding here. So in example 1 we have 3 sub questions, so let's see some of the question we have here. Okay, so let's see here. A, we have an elevator is carrying a man of 70 kg upward, accelerating at a constant acceleration from rest to 10 meter per second in 2 seconds. Find the size of normal contact force on the man. Okay, so let's illustrate the problem here. So we have an elevator like this, represented by a larger box over here, and then we have small box represent man here, and it standing in the elevator. Alright, so basically the man is on the floor of the elevator. Right, so for this case, yes, we have vertically downward, we have weight force from the man to the floor of the elevator. It is 700 Newton. And then normal reaction force from the floor of the elevator to the man acting up vertically, we have normal reaction force denoted by capital R. Okay, so the system is accelerating up, okay, from initial velocity of 0 meter per second to a velocity of 10 meter per second in 2 seconds. Alright, so the question asks to find size of normal contact force on the man. So basically we want to solve for the R here. Okay, normal contact force from the floor of the elevator acting to the man. Okay, so for this case, what we're going to do is we will find the acceleration first, because we're going to apply second Newton's law in order to find the R after this. Okay, so find the acceleration. So how to find the acceleration? Again, we have initial velocity, we have final velocity, and we are given the value of t. So we will use v equals to u plus at to find the acceleration. So v is 10, u is 0, plus with a, the thing that we find, multiplied by 2 seconds. So a is equals to 5 meter per second square. Okay, alright, so for this case, the motion of the system is upward, so I assume upward is positive for easier calculation. So for this case, we're going to get R is positive because the direction of normal reaction force is acting up and same direction of motion. So in our equation, it will become positive, and the weight is acting opposite direction of motion. Then in our equation, we're going to put negative 700 for the weight and equate with 70 for the mass multiplied by the acceleration that we have found just now. It is 5. So normal reaction force we will have here, it is 1050 Newton. So there is normal reaction force acting to the man from the floor of the elevator with a magnitude of 1050 Newton. Alright, this is solution for question A. Alright, for question B, we have an elevator is carrying a woman of mass 55 kg upward. It is traveling up at 8 meter per second and start to slow down at a constant rate when it is 9 meter from where it stopped. Find the size of normal contact force on the woman. Okay, so let's illustrate with a diagram here. So let's put here for question B. So we have a woman on the elevator again. So we have a woman with small box, and the weight here, given the mass is 55, so the weight is 550 Newton, and there is normal reaction force acting from the floor of elevator to a woman acting up vertically, denoted by R. Okay, and the elevator is accelerating upward with a constant acceleration. We don't know the value, but we know that initially the speed is 8, and then it travels for 9 meter, and then after that it stopped for final velocity is 0 here. As you can see, initial velocity is 8 and final velocity is 0, so you can expect the value of acceleration will be negative. Right, so first thing first, we need to find the value of acceleration. In order to find the normal reaction force, we need to apply second Newton's law, but we need to have first the value of acceleration. Right, so for this case, we need to find the acceleration by Suvat equation. So by Suvat equation, v square equals to u square plus 2as. We're going to get the acceleration here. So final velocity is 0, initial velocity is 8, so square it, plus with 2 times acceleration multiplied by distance travel from 8 meter per second to 0 meter per second. It takes 9 meter, right? So displacement here is 9. So we're going to get the acceleration is negative 32. Negative 32 over 9 meter per second square. please check this value. Alright, and then after that, when we get the value of acceleration, check carefully, and the acceleration is negative here, and it is logic enough because as you can see, the initial velocity is 8 and the system reduced its velocity to 0 meter per second, so you should have negative value of acceleration. Alright, and after that, when we have the value of acceleration, then we apply second nature law here, F equal to ma. So what force involved here in the system? So we have weight force vertically downward and normal reaction force acting upward. So since direction motion is upward, so upward is to be positive here, so normal reaction force is positive, minus with the weight, it is negative of course, so R minus with 550 equals to mass of the woman 55 multiplied by the acceleration that we have calculated just now, so negative 32 over 9. So for this case, we're gonna get normal reaction force is equals to 354 Newton in 3 significant figure. Okay, that's it for question B. Please make sure you try yourself also. Right, so for question C, I leave for you to try. Okay, please try this question by yourself, and the answer for this is R is equals to 604.8, or in three significant figure we have 605 Newton. Okay, make sure you try this question so that you have better understanding. Okay, now let's move to the next question. Example 2. Alright, so simple example here. Let's say we have a weightlifter is trying to lift a bar with mass 200 kg from the floor. He lifts with a force of 1800 Newton but cannot lift it off the floor. Find the size of normal contact force from the floor on the bar while the weightlifter is trying to lift the bar. So let's illustrate the problem here. So we have floor and there is a weight bar over there of mass 200 kg. So we have weight of the bar is 2000 Newton acting vertically downward, and then the weightlifter try to lift the bar with force of 1800. So there is a force from the weightlifter, that person, with 1800 Newton. And other than that, remember the bar still on the floor, right? So means that there is a contact between the surface of the bar at the bottom to the floor. So means that there will be a normal reaction force from the floor to the weight bar. Okay, it is denoted by normal reaction force R. That is our complete force diagram. We have weight vertically downward 2000 Newton, and then force from the man try to lift with 1800 Newton, and then there is normal reaction force from the floor acting to the bar with force of R Newton. Okay, so for this case the object is not moving, right? The object still at the floor because say that cannot lift it off the floor, right? So for this case, summation of force is equal to 0. Why it is equal to 0? Because there is a motion vertically up. Then we apply this formula. So just summation of force equal to 0. So what force over here, we consider all of it. For this case, I assume upward as positive for our reference, even though the object is not moving, but this assumption just for our reference. Okay, so any force same with this direction of motion, with this direction of assumption is positive, and any force that opposite direction of this assumption become negative. So we're gonna get R plus with 1800, both of it positive because we assume as positive. So these two force acting same direction of assumption, and then we have weight vertically downward 2000 Newton, and then all of it is equal to 0. So normal reaction force here is equals to 200 Newton. That's it. As I said just now at the early of this subtopic discussion, I said that normal reaction force is not necessarily equal to weight. Yes, this is one of the example. If there is external force on the object, then we need to consider all the forces and object to find the normal reaction force. Okay, so be careful. Normal reaction force is not necessarily equal to weight. Okay, right, that's it for example 2. And for example 3 is actually from the textbook, so hopefully you can check yourself this example 3 in the textbook and make sure you try yourself. And then after that, to the next page, we have try questions. So this also I just took from the textbook exercise, so hopefully you can try this one and you can discuss with the other class member for the answer. Right, so that's it for now. Thank you very much everyone. See you in the next video.